All right, so example 3, we are going to, I'm just going to write our equation that we had from yesterday. When we are looking at the equation for the slope of a secant line between P, our chosen point, and any other Q, the equation we have is f of x, any x, so that represents our QY value, minus f of A, that represents our Py value, the y coordinate, over x minus A. Okay, so now if we look at this velocity graph, suppose that a ball is dropped from the observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 5 seconds. Hint from Galileo, we know that the distance fallen, s in meters, is dependent on the time t in seconds given by this equation. So we are looking at a projectile motion essentially. Right here is the tower. And you're standing on here and you throw something. Okay, so it looks kind of like a parabola going down. And so what we want to know is what is the instantaneous speed of the ball after 5 seconds. Okay. If I change the language in here, using the letter D for distance and T for time and V for velocity, this is telling me that the distance equals 4.9 t squared, right? If I have distance and time, how do I find my velocity? What's the equation for velocity? Try again. D over t, right? So it is the rate of change. It is the derivative. It is the slope, right? Your y values, the distance over the time of your graph. So we're looking for what is the slope of my distance graph after 5 seconds. So using language, can you visualize what I'm trying to say? Do we understand the concept before we do the math? Yes or no? Can you shake your head? Nod or shake? Okay, good. So what we're going to do is 5 is my key point. That is my A value. Okay, and this is my f of x. Remember, f is a letter, x is a letter. We can put whatever letters we want. We can call things different things. We don't want to get hung up on the f of x. And then we see an s and then we're like, oh crap, I don't know what I'm doing. It's the same thing. Okay, so when I do the equation and I put these ideas into here, what would that look like? F of x, or in this case, S of t, would be 4.9 t squared minus, my key point is at 5, so this is going to be 4.95 squared, right? That's my distance at 5 seconds, divided by t minus 5 seconds. Are we happy with that? Okay, now in a perfect world, if I said this is a no calculator question, you would need to simplify this and blah, blah, blah. But since we have calculators, let's not worry about simplifying right now. Let us just type this in. Actually, you know what? Let's just simplify this bit right here. That way we have less typing to do when we get to our calculators. This is going to be 4.9 t squared minus, can you guys tell me what number that is? 122.5. Okay, so we're going to type this into our calculator as the y1 value. Remember to keep numerator and denominator in brackets. And then we are going to go to a table of values to see if our slope is the same from the left and the right. So we are going to approach 5 from the right. So we're going to choose numbers bigger than 5 and get closer to it from the right side. So we're going to start with 6, 5.5, 5.1, 5.001, and etc. Things like this. We don't want to touch 5. We just want to get very, very close to it. And then we're going to do the same thing with the left side. So I'm choosing to start with a number smaller than 5, such as 4. Right? And I'm going to get closer to 5, 4.5, 4.9, 4.99, just to give an effect. What's the effect here? So going to my calculator. Some of you have already started. 4.9x squared minus 122.5. X minus 5. Okay, so once you have your equation typed in, I'm just going to double check my brackets. Make sure I have an x squared there. Good. Now I'm going to go second table. And I'm going to type in some numbers. Let's see, 5. Oh, I need to change my table set. Make sure that your independent is set to ask, not auto. There we go. Okay, so I'm going to start with 6, 5.5, 5.1, 5.001. Okay, so looking at my chart, approaching 5 from the right, so choosing bigger numbers and coming in closer, I see 53, 51, 49, 49, 49.005. So you can see here 53, 49, 49, 49.05, and the 49.005 is going, we're essentially getting closer and closer to 49, right? So this is saying as we approach 5 from the right, and we're going to use a little plus sign as an exponent to signify we are larger than 5, getting close to 5. Our velocity approaches 49. On the other side, as we approach 5 from the left, now because we're smaller than 5, I'm going to use a little minus sign, saying I'm approaching 5 from the left side. Hopefully you can see it is going to get closer and closer, oops, to 49 as well. So 44, 46, 48 point something, and it's going to eventually get to 49 at some point. So this approaches 49. So what this is telling us, that on the number line where 5 is, as we approach from the left and as we approach from the right, we are from both sides approaching the number 49. Okay, so that is telling us that the derivative, the slope at that point, is going to be 49. So how am I going to write this? The limit as x approaches 5 of 4.9 t squared minus 122.5 over t minus 5. So as x approaches 5, for this equation, the result is 49. However, this is a word problem. What does 49 represent? Velocity. So what am I going to call it? What's my units for it? Meters per second, and this is instantaneous. Instantaneous means in the moment. Only at 5 seconds is it moving 49 meters per second, right? So instantaneous velocity at t equals 5 seconds. Because when an object is falling, what do we have to consider when we're thinking about its speed? Gravity. Gravity is what? It's an acceleration, right? So the less time, the less acceleration, it's going slower. The more time it has to fall, the faster it's going. So only at this time can we say that the velocity is 49. And that's the idea behind tangents. Tangents only apply to a curve at one point because everywhere else on the point, something is changing. Okay, so that is lesson 1. I'm going to pause our recording so that I can just attach